Welcome to our presentation on fast private kernel density estimation via locality sensitive quantization. Let's start with kernel density estimation, KDE. This is a commonly used method in machine learning and statistics to turn a discrete dataset in R to the D into a continuous density function over all of R to the D. For example, here you can see the histogram of a two-dimensional dataset where the size of each circle represents the number of data points that follow those coordinates. And on the right, you can see the KDE constructed on this dataset. And this is done as follows. We take the Gaussian kernel, which measures the similarity between every pair of points in R to the D as e to the minus their squared Euclidean distance. And then we define the KDE at each point as the average of its Gaussian kernel similarity with every point in the dataset. This is equivalent to placing Gaussian centered at each of the data points, and then the KDE is just a mixture of those Gaussians. In this work, we are interested in differentially private KDE, or DPKDE. Differential privacy is a notion of privacy commonly used today in machine learning. The setting is as follows. We have a data curator who has a private data set of endpoints in R to the D, and she can define the KDE on this data set. And her goal is to release a function k tilde, such that on one hand is epsilon dp with respect to the dataset, so it preserves the privacy of every data point. And on the other hand, it approximates the true KDE function of this dataset in the following sense, that a client that has access only to this k tilde and not to the original dataset can still use it to accurately estimate the KDE at each point in R to the D. For example, here in the bottom, this is a real data set of hospital visits by diabetic patients, and we may need to protect their private medical data while doing data science or machine learning on this data set. So if the client were to draw samples from the DPKD distribution, he would get a synthetic sample of hospital visits that never happened, of patients that do not exist, which nonetheless has similar statistical characteristics to the original data set without disclosing any private information. Our main results for this problem are as follows. In the high-dimensional case, we get a DPKD mechanism with running time which is linear in the dimension D, so it does not suffer the curse of dimensionality and is feasible for high-dimensional data as opposed to prior work. And in the low-dimensional case, we get a DPKD mechanism with error of order 1 over n, so it decays nearly linearly with the number of data points, which is better than prior work. And we have some other results in the paper, but this talk is going to focus on the Gaussian kernel. Let me be a bit more precise in the comparison to prior work. So there are several existing DP mechanisms that can be used for DPKDE, and they achieve the results that you see on the first line. Two notable exceptions. One achieved the weaker notion of differential privacy, known as epsilon delta DP, or approximate DP, but with better error rate that decays like 1 over n. And the other achieved running time linear in the dimension D, so no curse of dimensionality, albeit not for the Gaussian kernel, but only for a restricted family of kernels known as LSH kernels. And what we get in the high-dimensional case is the same result for more kernels, including the important case of the Gaussian kernel. And in the constant dimensional case, we get this better linear error decay rate, but with pure or epsilon differential privacy. Let me say a few words about our techniques. They are based on a notion that we call locality sensitive quantization, or LSQ, which is a way to express a kernel using few bounded and sparse features. I don't have time in this talk to go into the formal definition. It is in the paper, of course, but let me tell you why it is useful. On one hand, LSQ is sufficient to imply efficient DPKDE, and on the other hand, we can actually construct LSQ, and this actually comes from familiar methods for efficient KDE in the non-private setting. So specifically, from random Fourier features, we get our high-dimensional result. From the fast Gauss transform, we get our low-dimensional results. And from locality-sensitive hashing for kernels, we recover the results from prior work mentioned earlier for LSH kernels. So all of these things fit into the LSQ framework and give us DPKDE mechanisms. Finally, let's see some experiments. Let's start with the low-dimensional case. This is the same two-dimensional data set that we've seen before. On this plot, you can see the privacy parameter epsilon on the x-axis versus the KDE approximation error on the y-axis. And on the right plot, you can see the mechanism running time on the x-axis versus the error on the y-axis. Our mechanisms are compared to prior state-of-the-art and to a naive baseline. And as you can see, indeed, our low-dimensional mechanism has the best performance for this low-dimensional dataset. This is the same dataset and the same mechanism that we've already seen visualized earlier in those heat maps. And these are the same plots with the high-dimensional dataset. Here only our high-dimensional mechanism is feasible along with the baseline due to the high dimensionality. And as you can see, it gets good performance. So this is it. Thank you for watching and listening. And for more, please see our paper and the accompanying materials.